Welcome to The Explainer. Today, we're pulling back the curtain on one of the most important concepts in modern computing, the Paxos algorithm. This is the secret sauce, the invisible backbone that lets massive computer systems all agree on a single truth, even when everything seems to be going wrong.
Okay, let's just dive right in. We have to start with this really fundamental problem. I mean, think about it. When you have dozens or even thousands of computers all trying to work together, how on earth do you make sure they're all on the same page? How do they reach a consensus on what's true? Especially when you know for a fact that messages will get lost and machines will just crash.
And to make this super real, just think about your bank account. What if one computer says you have $100, but another one says you have 50? That's not just a small glitch. That's total chaos. The system has fundamentally failed. And that is the exact kind of disaster that Paxos was designed to prevent. It's a protocol for reaching agreement no matter what.
So, let's put a more formal name on this. In the world of computer science, this is known as the consensus problem. It's all about one thing: getting a whole group of independent computers to agree on one single value.
Now, to solve this, any algorithm worth its salt has to follow 3 super strict safety rules. First off, the final decision has to be one of the values that was actually proposed. The system can't just invent an answer. Second, and this is the big one, only a single value can be chosen. No split decisions, ever. And third, the system can't lie. A computer only finds out a value was chosen if it really truly was. These rules make sure the system is always correct.
All right, so to really appreciate how elegant Paxos is, let's start with a much simpler idea, and then watch it break. We're going to need to introduce 3 key players in this little drama.
First up, we have the proposers. These are the ones who get the ball rolling. They've got a value, an idea that they want the whole system to agree on. In our little story, you can think of them as scribes trying to get a new law written down in the city's official records.
Next, we have the acceptors. These guys are the voters. They're the ones who receive the proposals and get to decide whether to accept them or not. So let's think of them as a council of elders. For any new law to pass, it's got to be accepted by a majority of this council.
And finally, there are the learners. Their job is pretty simple, actually. They just need to find out what the Council of Elders decided and then go tell everybody else. They're like the town messengers, spreading the news of the final decision to the rest of the system. So the easiest way to do this? Just have one acceptor, right? A single, all-powerful elder who makes all the decisions. But that creates this huge, glaring vulnerability. If that one acceptor fails, if that one elder gets sick, the entire system just grinds to a halt. Game over. No new decisions can ever be made. That's a single point of failure, and that's exactly what we're trying to avoid here. Okay, so a single elder is a terrible idea. The obvious fix, then, is to have a whole council of them. And that works. It makes our system way more resilient. It solves that single point of failure. But as you'll see, solving one problem can sometimes create a brand new one that's a lot more subtle. With multiple acceptors, we're safe from one machine crashing the whole thing. But what happens if 2 scribes propose different values at the exact same time? Scribe A says the official color should be blue. Scribe B says it should be red. Half the elders vote for blue, half vote for red. Uh-oh, no majority. The whole system is just stuck. It's in a deadlock. So how do you break the tie and actually guarantee an agreement? So how do we fix this mess? Well, this is where the genius comes in. The solution is to add a little bit of order. Every single proposal gets a unique increasing number, kind of like taking a ticket at the deli. And this leads to a critical rule. Once a majority has chosen a value, let's say they've chosen blue, the system is locked in. Any future proposal with a higher number has to also propose blue. The system is not allowed to change its mind. And that's the key to stopping that split vote chaos. But wait a second, how can a new proposer possibly know what value was already decided? It can't just guess. Well, this is where the core logic of Paxos clicks into place. Before a proposer can even suggest a value, it has to do its homework. It has to go out and check with a majority of the acceptors and ask them 2 things. Hey, have you already promised to vote for someone else? And if you have, what value did you accept? Only then can it make a new proposal that actually respects what's already been decided. And this whole idea, this logic of checking first, then proposing, leads us straight to the elegant 2-phase protocol that sits at the very heart of the Paxos algorithm. So in the first phase, which we can call the promise phase, a proposer picks a new number, n, and sends out a prepare request with that number to the acceptors. An acceptor gets this message, looks at the number, and if it's higher than any other proposal number it's seen before, It makes a promise. It says, okay, I promise I will not accept any proposals with a number lower than n. And it also tells the proposer about any value it might have already accepted in the past. So once our proposer gets that promise back from a majority of the acceptors, it can move to phase 2, acceptance. Now it sends out an accept request to those same acceptors. And this message has both the proposal number n and a value. Now, if the acceptors haven't broken their promise in the meantime by listening to some other proposal with an even higher number, they officially accept the value. And if a majority of acceptors accept it, boom, consensus is reached. That value is now the chosen one. Now, this whole process leads to a really interesting and important distinction. Paxos is designed to guarantee safety above all else. That's what you see on the left. It means the system will never make a mistake. It will never, ever choose both red and blue. It's always correct. But look at the column on the right, liveness. Paxos doesn't actually guarantee that a decision will be made at all. In some really rare cases, the system can actually get stuck.
So why can it get stuck? Well, you could have a scenario with two proposers locked in this endless battle, right? Proposer 1 gets promises for number 10. But before it can send its value, proposer 2 swoops in and gets promises for a higher number, 11, which invalidates the first attempt. Then proposer 1 comes back with number 12, and on and on and on. They get stuck in a loop. So to solve this and make sure things actually move forward, real-world systems elect a single distinguished proposer, basically a leader, who gets to be the only one making proposals for a while.
Okay, so why does any of this matter? I know this all might seem a little abstract, scribes, elders, promises, but this algorithm is the foundation for so much of the technology we depend on every single day. Let's connect it to the real world. The number one application of Paxos is a technique called state machine replication. Now, it sounds complicated, but the idea is actually pretty simple. If you have a group of servers, you can use Paxos to make them all agree on the exact same sequence of commands. Command 1 is X, Command 2 is Y, Command 3 is Z. And since they all execute the exact same commands in the exact same order, they all end up in the exact same state. They start acting like a single, ultra-reliable, fault-tolerant supercomputer. And believe me, this is not just theory. Paxos and algorithms inspired by it are running the absolute core infrastructure of the world's biggest tech companies. We're talking about the globe-spanning databases from Google and Amazon. We're talking about financial systems where getting it wrong is not an option, and the coordination services that literally keep the cloud from falling apart. And that kind of brings us to our final takeaway. What Paxos really shows us is that achieving agreement, especially in a world with uncertainty and failure, is a fundamentally hard problem. It doesn't just happen. It requires a clear, rigorous, logical process. It's this beautiful blueprint for how agreement can be solved, which kind of makes you wonder about the much messier world of human consensus, doesn't it?